Our next speaker, I'm delighted, is Professor Paul Bates, who is Professor of Hydrology at the University of Bristol, where he specialises in the science of flood modelling. Previously, Paul was Director of the Cabot Institute and Head of the School of Geographical Sciences at Bristol. In 2019, Paul was made a Commander of the British Empire, a CBE, so a very high achiever we have next to talk to us. And we expect a talk of that quality too.
Thank you.
Over to you, Paul. Thank you.
That's great. Thank you very much. And good morning, everyone. So I'm going to talk a little bit about one specific hazard. It's the only one I know much about, and that's flood risk. And we heard at the start that our latest best consensus information on flooding is provided by IPCC AR6. So what do we know from that? Well, we've got good confidence that we're going to, in the future, have more wet and more dry periods, so an intensification of the hydrological cycle. We also know that more places are going to see increases in flood and drought than are going to see decreases. We know that as the climate warms more, those effects are exacerbated, and we know that flood and drought is going to impact a wide variety of sectors. Beyond that, though, we find it difficult to make more detailed statements. I'll try in a few minutes just to outline what we know about flooding and also what we don't know, or at least what we don't know yet. But if we do have good information about how the climate will change into the future, the purpose of this image is to say that we now, as a result of developments over the past 5 or 6 years, have models that can take future projections of climate or observations of current climate and translate that into really detailed flood inundation predictions. And this is one of the first ones that we did at Bristol. This is a global 100-metre resolution map of the area at risk of the 1% annual chance flood, otherwise known as the 1 in 100-year flood. So let's just think about that. Met Office climate models are great, but their grid scales are about 100 kilometres. This is a global model with a horizontal grid scale of 100 metres. And from it, we can produce maps of flood hazard over Africa, and we can give these to national governments or NGOs or to insurers to try and help with their risk management. And we can do that change over time. So here's a more recent bit of work that we've done in the States. This is taking a particular climate model ensemble called CSIM and projecting what that means for future coastal, pluvial and fluvial flooding across the US. So this is the change in number of properties at risk between 2020 and 2050. And for this particular climate model ensemble, you can see an interesting geography to this. Of course, I would say that as a geographer, wouldn't I? But you see actually reducing flood risk over central and southwestern states in this particular set of climate projections, but increasing flooding around the coasts as a result primarily of sea level rise, but also an intensification of hurricanes. And we're getting drying in the centre because although rainfalls are going up, that's being counterbalanced, at least in these locations, by a drying out of soils. So the more intense rain that's falling is falling onto drier soils, drier antecedent conditions, and less runoff, therefore. So we can do all this kind of really fancy high-resolution projection. This one is based on a 30-metre model over the entire US. But as I said, with the climate projections we have currently, we find it difficult to say, we can make general statements that flooding is going to get worse in more places than it's going to get better. We're going to see it's going to get worse with more warming. But we find it very difficult to say exactly what is going to change, when, where, and by how much. And as we zoom in, we see real limitations in what we can do with our current generation of climate models. And the problem there is that the set of climate models that the IPCC use, which are known as CMIP, Coupled Model Intercomparison Project. CMIP class models really struggle to predict intense precipitation changes. Let's not get into the detail of this too much, but this just illustrates projections of rainfall across the tropics. This is a satellite. TRMM is a satellite observation of rainfall across the tropics, in this case during El Nino events. You can see the scale is in millimetres per day. And these are the biases in the last 4 generations of CMIP climate models. So these are the differences between the observations from CMIP 3 all the way down to CMIP 6, which is our current set. What you can see is that, firstly, the biases are the same order of magnitude as the signal. So the bias, the error in the model, is as big as the signal that we're trying to see. And secondly, the pattern that the model predicts is almost the inverse to the observations. And this has not improved over nearly 20 years of climate modelling. The problem here is that these models operate at grid scales which are much greater than the length scales of precipitation patterns in the atmosphere. So with a 100-kilometre grid, you can't really resolve convective precipitation and the kinds of atmospheric processes that lead to the most intense downpours. So later on today, in fact it's embargoed to 4 o'clock this afternoon, so I can't show an image of this. I and a group of other scientists are publishing a paper in Nature Climate Change calling for a new international consortium to develop a new generation of climate models at kilometre scale resolution. So if you're interested, have a look on the Nature Climate Change website after 4 p.m. The paper is led by Dame Julia Slingo, who's a former chief scientist of the Met Office. So that's what we know about physical hazard. But I want to raise one other key uncertainty that we have in our projections of future flood risk. And that is that we have a very limited ability to project future exposure and vulnerability at present. And to illustrate this, I put up this is a satellite map of Venice from Jet Propulsion Lab. And you can see the complex geography and changes in building density quite nicely. You see the intense building core over the island of Venice, but also on the mainland of Italy as well. So that's what we know that population looks like in reality. And these are 2 future population projections from the same region from our current best global future population data sets. You can see these are way too smooth. They look nothing like reality. And the problem is, if you intersect those populations with maps of flooding, you generate huge biases, because in these population projections, you're smearing people out across the landscape into flood zones, when actually humans are much more intelligent. They tend to try and avoid, but not completely avoid, building in areas that get regularly wet. So this is problematic. We have tens, maybe hundreds of thousands of scientists working on the physical basis of climate change. I'm one of them. Yet we probably have a few tens or a few hundreds working on population projections. And every time we do an analysis of what's the biggest driver to future risk, and comparing population and climate change as drivers of change, we find that population change outdwarfs climate change as a driver of future risk, normally by a factor of 3 or 4. So we've got a really big uncertainty that we're doing relatively little about currently. And therefore we need to bring together both social scientists and physical scientists in order to solve this problem. Thank you very much.